Okay, so in R2, what was kind of the, in general, in R2, meaning the xy plane, what's kind of the general idea of what it takes to write the equation of a line? So we want all points that follow a linear pattern. And so what are the key elements of that? It's one of the key elements of that. Okay, so slope is true, but what's a more profound way to talk about slope? It's deep, more meaningful. Rate of change, right? So the rate of change, and also, if you have the rate of change and a point on the line, that would determine a unique line, right? So my rate of change is 1/3, and it actually did go through that point. Try again. So and it goes through this point. That would determine a unique set of points that followed a linear pattern, right? A rate of change and a point. So in R3, the same holds true with the point. So we could start with a given point. But what is rate of change in 3 dimensions? So we can talk about that, but it's not just a simple kind of quick conversation of, oh, the rate of change means this. So rather, what can we use? So if you imagine this point is on some line, which is a set of points like this, then what would be a really simple way then to say, hey, we need something like the rate of change that's going to determine all points on a given line. Hint, it's been the whole topic of this course so far. A vector, right? So if we had a vector that pointed like, a vector would give a direction, right? A vector in R3 would give a direction. Along with that point, then would generate a set of points in space. And so let's see how that works. So here's a point, 3, -3, 2. So I'm showing the point 3, -3, 2 here. And our direction vector that I'm going to use is -1, 2, 1. Okay, so the first thing we're going to do is we're going to rewrite that point as a standard position vector. Remember what that was? What's a standard position vector? Yeah, at the origin. So I'm going to put the tail at the origin. And so now what is that standard position vector? So if this is the point 3, -3, 2, then that vector is 3, -3, 2, right? Okay, and so then where does the vector come in? So what I'm going to do is I'm going to take this what we call direction vector for the line. I'm going to put its tail at the tip of my standard position vector for my point. So that looks like this. Okay, so there's the vector -1, 2, 1 with its tail at the tip of my standard position vector for my point. Does that make sense? And so that just generated a new point on the line. Do you see what point? So this is the vector, -1, 2, 1. So what? I just got a new point on my. I just got a second point on my line. What is the second point on the line? Was it? She wants 2. 2. I think she had the right idea. 2, -1, 3. Right? Because it'd be the sum, right? It'd be the vector sum of that standard position vector for the point and the direction vector. If we add them together, would give us a point. So we think about this as generating points on the line as vector addition, right? The sum of those two. And so what vector is that? 2, -1, 3, right? And so now we have 2 points on the line. We have the point 3, -3, 2. And now we have a new point, 2, -1, 3. Is the point -1, 2, 1 on the line? Maybe, but not necessarily, right? Not necessarily. This is the vector that gives us the direction, right? Okay, so now how could we get another point on that line? You're doing something visual. So what were you thinking? Do another one. Attach another direction vector. Yeah. So he said take the direction vector and put it again here. Would that give me a second point or a third point on the line? All right, so what's another way to say that? Taking this vector and then duplicating it. What's another way to express that? Maybe as one vector now. Scalar multiplication by 2. So if I took my standard position vector for my point and added 2 times the direction vector, I'd get another point. Okay, so this is the idea. And so let's do this. Let's make a little table here. So really, we're talking about what? Taking scalar multiples of this vector added to the standard position vector for the given point. And if I took every scalar multiple of that, I'd get every point on the line. Do you see that? So let me just show that. Good question?
Yeah, when you're saying the line, you're meaning that direction vector, right? The V.
No, the line is a set of points. Like it's a set of points in a linear row.
Right, but you're talking about in reference to that direction vector V, right?
The direction vector V will point in the direction of the line or be parallel to the line.
Okay.
So I got a point, and then I've got this direction vector that's parallel to the line, and I'm going to use it to generate points on the line. So here's how it kind of works. So this is, I'm showing now for a scalar multiple of 1. So if I start scaling like you guys were talking about, every time I scale it, I'm going to get a new point, right? Or I could scale it negative, right? See that? So this is going to generate, all scalar multiples of the direction vector are going to generate the points on the line. So that looks like this. So then all those points look like this. All right, so the scalar, so normally we say the scalar multiple is, we call it normally t. Okay, and so then we started with t being 1, and t being 1 meant that was right there. That was that first point we generated, and that's just simply going to be what? We're going to do 3, negative 3, 2, and then what? Plus 1 times, there's my blue vector, right? Negative 1, 2, 1. And what did that equal in red? That was our 2, negative 1, 3. But now, so that 2, negative 1, 3, then the result is the standard position vector of the new point, right? So that's the standard position vector of the new point. So then you guys suggested t equals 2. So when we do t equals 2, we still start with the same point, 3, negative 3, 2. And then we're going to add what now? 2 times the blue vector, negative 1, 2, 1. And that's going to equal, so what's that? And let me show that situation. Right there. There it is. And you're going to get, what point is the new point on the line? Negative 2 and 3 is negative 1. No, is it 1? Positive 1, sorry. Positive 1. 1, so 1, 1, 4. All right, so you guys do one more. So you guys generate the point for, say, negative 3. So what point will you get when you scale the direction vector by negative 3? the notation? I forgot the notation. Yeah, whatever. Okay. Just say it's P. So what'd you guys get for that? Let's make sure we're on the same page. 6, negative 9? Negative 1. Everyone got the same thing? All right, so this is right? Okay. So basically, what is the vector function of a line? Every point, so this is every point, right? Every point is equal to the vector for our known point plus every scalar multiple of the direction vector. Then gives us every point on the line. So let's write that out. So it'd be x, y, z, what that represents every point on the line equals a given point. We could say x naught, y naught, z naught plus t times, oftentimes we'll use for the direction vector, say a, b, c, what we call v. So this, and so this is represents, you should know what everything in there means. So this x, y, z, variable or fixed? X, y, z, this one right here. That's every point on the line. It's representing every point on the line. This one, x naught, y naught, z naught. Fixed, that's some given point. That's going to be numbers. You're going to know those, right? T, variable or fixed? It's how we're going to scale the direction, right? And then the ABC. We know it, right? So we know it. We know that by scaling the direction vector and adding it to the original point, we get a standard position vector pointing at every point in the line for every value t. So you generate points by changing t, right? Change t. Every time you change t, you get a new point on the line. Okay, so notice this is vector addition, so we can do the math here. So if I did the math on this, I take this vector plus t times that vector, what one vector would result? So coming up here, so what one vector would equal x, y, z if I actually did the vector addition and scalar multiplication on the right? So the x component would be x naught plus ta, then y naught plus tb, and z naught plus tc. And so then we can take this out of vector form by writing each component separately. What's the x component? X equals x naught plus ta, and then y naught plus tb, and z equals z naught plus tc. Okay, and so this is a different way to write a line, and that should look familiar from Calc 2. What kind of thing is that from Calc 2? Do you remember? What kind of function is that? It's a parametric function, right? So this is the parametric form of a line. It's considering each component of the vector separately, so there's no more vector anymore, right? So this idea of a parametric function and a vector function are like twin brothers or twin sisters. They're like one and the same. It's just a different form of writing the exact same thing. So this is the parametric form of writing the equation of a line. And this one's called vector form. Okay, so you should be, so where do you, so in this one, where do you see every point on the line? Where do you see the given point, and where do you see the given direction? Tell the person next to you. Where do you see every point? Where do you see the given point? And where do you see every, or so the direction vector for it? Go. Just take 30 seconds. Okay, don't make sure I don't forget anything here. All right. Okay, so where do you see every point on the line? X, Y, Z generates every point on the line. Where do you see the given point? They're separated up, right? It's still the X naught, Y naught, Z naught, but now you get each component in a separate equation. And then the direction vector? ABC, okay? All right, any questions on it? So this is vector form. We see where it's come from. We know how to generate points. And then this is parametric form. Okay, so how can you test whether a point is on a line or not? So say I said 10, this point is the point. Did we ever write? So we never wrote the equation of this line. So, which is easy. So write the equation of this line. Say, write the equation of this line in parametric form. Go ahead, write the equation of this line in parametric form. Everyone do it? Write the equation of this one that we did in parametric form. And now, how could you figure out, is the point 10, negative 8, negative 1? Is that a point on this line? How can you find out? So why don't you work on that little task, see how you could figure out. So you've got the line in parametric form, writing in vector form. So write it both ways. I mean, sort of write the line in both ways, and then think about, if I gave you a point and I said, is that point on the line or not? What would you do to figure that out? 10, negative 8, negative 1. Here's our line in, I wrote our line in vector form down there. And then, so hopefully parametric form wasn't too bad. So how would you figure out if 10, negative 8, negative 1 is on the line?
First find T. See if it applies to the Y and Z.
So he wants to find the T value that would make X 10. What T value makes X 10? Negative 7? So, if this point's on the line, then negative 7 ought to make Y negative 8, and it ought to make Z negative 1. And I would bet a lot of money that it doesn't, because I just came up with this point off the top of my head, right? Okay, so it should not. So, you have to have, the same T has to give these three, at any T, single T that gives you an ordered triple is going to be a point on the line. If it doesn't, if you've got three numbers which would require different T's for different coordinates, then it can't be on the line. So, no. All right. Is this the only way to write the equation of this line?
No.
Give me another way to write the equation of this line. So here's x, y, z equals 3, negative 3, 2. What's one way that I could write this in a different way?
Points minus the original points.
So I don't want to change the form. I want to keep it in the same form, but I want to represent the points in a different way, but keep the form the same. Yeah.
Do you mean adding the two vectors to adding the vector?
No, I want to keep it in this form. I want to keep it in this form. Yeah.
You can make you can scale the other vector, not the original point vector, but the other vector by 2, so you can do negative 2, 4, 2.
Okay, is there more than one direction vector that would indicate the direction of this line? How many are there? Yeah, so all I need is any vector that's parallel to -1, 2, 1 is going to be a legitimate way to get the points in this line. So give me one way I could change this. So I got -1, 2, 1. I could do -2, 4. It's got to be parallel, right? I got to have a parallel vector to this one. So -2, 4, 2. How about -200, 400, 200? Okay. How about 1,000, -2,000, 1,000? 1,000, -2,000, -1,000. Did I say it wrong the first time? Okay, good. Okay. So you got the idea, right? So 1,000. So if I did 1,000, so it could be the opposite direction too. So positive 1,000, -2,000, -1,000. Right? There's an infinite number of ways you could scale a vector to get a parallel vector, and any of those parallel vectors will work. How else could I change this? Any point on the line works, right? So give me another point on the line. We've already found some. 114 is easier to write. 114. So any point on the line and any vector parallel to that vector will form an equation that will generate the exact same set of order triples. So there's an infinite number of points and an infinite number of parallel vectors. So it's kind of like infinite times infinite number of ways to write the equation of a line. Because for every order pair you have here, every point on the line here, you have all the parallel vectors that you could write there. Okay, so any point that the line generates is a valid point to put in your equation and still generate the same line. Any vector parallel to a given direction vector is going to be a valid way to write the points on that line. Okay. But now as soon as you pick a point that's not on the line or a vector that's not parallel to your original vector, you have a different line now. Okay, you would be writing an equation of a different line. Okay, I think I've talked enough. So you've got some work to do here. See how far we can get. Work together. And then we'll regroup maybe with 5 minutes to go and see what questions you have. But you're either making progress or you're getting help. Those are your two choices here. Making progress or getting help. Anyone get my answer for number 1? I bet no one got my answer for number 1. Anyone put my answer for number 1? Do you need to change it so it's mine? Do you need to erase and write mine down? Do you want me to check or somebody have to check or check with the person next to you? But there's one possible answer. Probably different than yours. First of all, do you know what those three terms are referring to, first of all? Parallel would mean they have the same direction, right? Same direction. The same line would be the same set of points. And then skew is non-intersecting but also not parallel. Can you imagine that? Okay, so for instance, see this is a line here that goes the corner of the wall and the ceiling there is a line. What's a line that's skew to? What's skew to that line? Yeah, so the line for that, no, that's not good. This one. Okay, like this, right? It's not parallel to that one that I said, and it's not going to ever intersect it. So that's what's called skew. Okay, so what would be true if they were the same or parallel? We could knock this off right off the bat. Same what? Direction vector, right? Or parallel, right? Like the direction vector of one would have to be a constant multiple of the other. They have to be parallel direction vectors. And then we either have the same or parallel lines. So here we've got, so that's what you want to check first. Direction vectors. 2, -1, 3, and 4, -2, 5. Not looking good. Are those parallel? Okay. Oh, there's four cases. Okay. So these are not parallel or the same, because this is not equal to some scalar multiple of that one, right? Not the same, not parallel. What's left? Intersecting or skew. Okay, so how are we going to figure out if they're intersecting or skew? So anyone come up with some way? Yeah, Griffin.
If you set the x, y, and z equal to each other,
Okay.
for intersecting, they all have the same point. So if you took like your t value and you call that like v for the same, because you want that to equal the same, you set them equal to each other and solve. You solve the first one, you get like the t value would have to be equal to 1. You plug it into the rest, it won't come out to 1. So they're not the same. So then it could be intersecting because they wouldn't share the same point.
Okay, so you lost me a little bit in the middle there.
Okay. So if you set the x's equal to each other, like 3 plus 2t equals 1 plus 4s.
Okay.
But replace t and s with like v or something.
So are you saying that in order for them to be intersecting, the value of t would have to be the same as the value of s? That's kind of what you're assuming by doing that.
Yes.
Yeah, so that's the reason why this one was given as s. And this is a warning. In the web work, I think they give them both as t, and you have to watch out, because if they're intersecting, it's not necessarily like if they're intersecting at the point where t equals 1, it may not be s equals 1 that generates that same point, right? So you want to keep those separate as two separate variables. Yeah.
If you solve for t and like if you find equations for t and s and plug them in for like y and z, and maybe you would see if they have like the same points then.
Okay. So yes, that's like a substitution technique. Yeah.
Yeah, I was going to say, so in that equation there, solve for t in terms of s.
Okay.
And then in the next equation down, the y equations, you can replace t with s.
Like that?
Yep.
So negative 1 plus 2s. So that's true according to the x-coordinates. T would be negative 1 plus 2s according to the x-coordinates. And so then you want to...
See if 4 minus...
So for the y
4 minus
equals...
all that, negative 2 plus 4s over 2.
Okay. And where am I going now?
See if that equals 3 minus 2s.
So 3 minus 2s, and this one equals negative 2 plus 6x. Is that right?
No, 5 minus 2 is 1. 4 plus 1.
But I'm simplifying this, isn't it? It's negative 2 plus 6s, right? Okay, and so this is not the way I do it. So what you're thinking from here? So that seems to be the same, but this one's not. So we're saying they're skew.
They're skew because on the y equation it says 5 equals 3.
The y equation 5 equals 3.
If you add 2s to both sides.
This is wrong?
Yeah, this is wrong.
4 minus t. T. Oh, I see. This is 5. Is that what you're saying?
No.
4 minus this, plus 1 minus 2s. Yeah, 5 minus 2s, right? So they're skewed because that doesn't equal that and that doesn't equal that. I've never done it that way before. So maybe that's right. Is that where your conclusion is then? You're expecting this, when you plug the t in, you're expecting that to equal that. Is that what you're saying? And then when you plug it in, you're expecting that to equal that. And if they don't, they're skewed?
Correct.
Okay, that certainly might be correct. Here's just quickly another way to do this. You could solve, this is, I know for sure works. So again, x equals 3 plus 2t equals 1 plus 4s. Set the x is equal. Set the y is equal. this will give you what? A solution T and S. T equals something, S equals something. So that would be the value of T and S that together would make the X and Y's correct. Then what would you do? You take that T value and find out what Z is, get the Z, and take this S value and get the Z for line 2. And if those were equal, then it's intersecting. And if the Z's don't equal, then it's skew. So that I know works for sure. I've never thought about it this way. Do you want me to, does that make sense? Solve for T and S as a system of the X and Y coordinates. Take that T and S and check them for the Z's. If the Z's match, then you got intersecting lines. If the Z's don't match, not intersecting. Okay? Web work for Monday, written work for Wednesday. So let's do it. Yeah. So let's try it. So X and Z, when you do the X and Z equations, or the X and Y equations, doesn't work. Okay, so let's try let's try the, what? We want to do X and Z? Let's do X and Z. So this is 1 plus 3t. And 4 plus 5c. Five S. Okay, and so to get rid of the joy, let's do Y and Z. It'll be easier. Is it okay?
Yeah.
So we'll do 4 minus t. It'll be a lot easier to solve that system. Yeah, it'll be easier. 3 minus 2s. Okay. So multiplying by 3 and adding together, I think you get 13 equals 9 minus 6. So 13 minus S. S equals 0. That's easy. Say what would T equal? So then T equals 1. Is that right? So 4 minus 1 this equals 3, and 1 plus 3 equals 4. So now, this was what, Y and Z? Does these give the same X coordinate? So if that's true, you get X equals 5, right? And S equals 1, or Y, sorry, X equals 5 for the first line, and X equals 1?
Yeah.
So, skew.
Okay, that makes sense. Because because for being the same way, I think it might also.
Yeah, so S equals 0 and T equals 1 makes the Y and Z coordinates the same, right? It makes the Y coordinates, what, 4? No, 3. So S equals 0 makes Y 3. And what does it make Z? 4 and Z 4. All right. So that's fine. But then it also has to make the X coordinates the same. It doesn't. T equals 1 makes this X coordinate 3, 5. Sorry. And S equals 0 makes that X coordinate 1. So don't equal.
Okay.
So skew.
So if it's parallel, it works in 2 directions, but not the third direction, it's skew.
No, don't make that assumption. Because you could have all 3. That was just this example. It happened that in the X and Y direction, these lines.
They were. Gotcha.
Right. So the one is like this. So the one is like this, and the other is pointing in the same horizontal direction, but there's different directions. If it's placed over here, then it's like this, right?
Gotcha.
Wait. So like this. Right. So these are. What is the direction? 2, -1. Okay, so both these lines point to -1. So they're both kind of horizontally in this direction. This first one, so this first one is like also up 3. This second one is up 5. But it could be over here, right? So they both have the same horizontal direction like this. And this first one is at an inclination of up 3. So, but this one over here is an inclination of up 5. Like that. So they never touch. But if you were looking down, okay, so if you were up here looking down on them, they would look parallel because they're parallel as if they were projected into the XY plane, they would be parallel. But you bring that Z coordinate in, and they have different inclinations, and they don't intersect.
It's kind of like this. Okay.
Yeah. Huh?
That makes sense. Thank you.
You're welcome. My pleasure. You too. And the YZ plane is the wall, right?
Yeah.
So 0, 4, 2.
That gives us the torque.
So this is 4 and 2. So only the 2 is contributing to the torque. The 4 doesn't contribute to the torque, right?
Oh,
Only the 2 is going to play a role here in turning the bolt. So you need, and this is 0.1. Right? So 0.1 times what equals the torque, which is 100 Newton meters.
That should be sine theta times force. Oh, here. Sine theta times force, right?
Well, that should be 1,000, right?
1,000? Oh, yeah.
So the resulting force has to be 1,000. So we're saying, what vector here makes that 1,000? So this is 1,000. No. Yes, 1,000, 2,000. So what is that? They're saying what vector? What's the length of that right there, right?
That's simple like that. Okay.
Does that make sense?
Yeah, but I use a way like a dot product to find this.
Well, it's not going to be dot product because this is a cross product problem. It might involve cross product, but it's not going to involve a dot product.
Yeah, I say I just use the dot product to find the degree and put it into cross product.
I'm not sure. You don't need the dot product to find the
Yeah.
angle. It's just this is just 1/2, so it's the inverse tangent of 1/2, right? So if you want to get the angle, you're talking about tangent inverse of 1/2.
Quick question: how do you use the bolt like this, like that? Or?
No, so it's like this is like a wall. The YZ plane is like a wall.
Okay.
And we're screwing the bolt in or out of the wall, right?
Yeah.
Like this. So it's like, so we're actually screwing it out or loosening it, right? Because we're turning it this way. So we're loosening the bolt by doing this.
Mm-hmm. And then the bolt goes in.
No, that's no, it's going to come out because right-hand rule, right?
Oh yeah.
It's going to be D cross F. So point your fingers in the direction of D so that they turn towards F.
Yeah.
Bolt will come out, and that's consistent because left, turn it counterclockwise, and the bolt comes out. Lefty loosey, righty tighty. So turn it right, and it gets tight. Turn it left, and it gets loose, and that's consistent with the right-hand rule.
Okay.
So the bolt's going to come out. But so do you see what I did for the problem here? So that it's the direction 2, 4, but we need. So to get 100 torque,